We'll start off with any questions off of the homework from yesterday, graphing those inequalities. Does anybody have any questions on those? Anybody else? Oh, we'll wait for you, Ezra.
So do we not use mixed numbers with inequalities, like for putting down the solutions there? I tried that once and it wouldn't accept the answer until I made it in proper fashion.
My math lab is really touchy about that. You know, if you end up with x is less than or equal to 2.5.
Yeah, one of the answers was like 25 nines, and that's how they want. That's the
Oh,
way they accepted it.
sure.
Something like that.
And realistically, that is an acceptable answer. But to get my math lab to recognize that that is all one number is kind of tough. When their templates pop up down here, there's one that's, you know, the fraction thing like that. There's a different one that's a mixed number. If you select that one and then enter, you know, the 2, the 1, and the 2 in there, it should take it. But sometimes even then it separates the 2 from the 1/2. If you type the 2 and then click this one and then enter the 1/2 in there, my math lab recognizes that as 2 separate numbers. There's a 2 into 1/2 and it doesn't always link them together.
Okay.
But yeah, the 9 over, or the 5 over 2 or 29 over 5 in your case, it'll always accept that. Unless it specifically tells you to reduce it to a mixed number, it should always accept the improper fraction. Yeah. Oh, yeah. There's a capital A instead of a little a. Yeah. Sure. And on homework, it doesn't matter. On homework, you're graded for completeness. You did it, is what happened with you there. If that happens on a quiz, let me know. And same with you, Ezra. If you're entering one, if you enter it as a mixed number on a quiz and it calls it wrong, let me know and I will change those grades. I try to go back in there and randomly check them, but I can't check every quiz, so it's a little clumsy. But if there's one that you think you got right, let me know. Part of that, when you go back and review the quiz, you got the problem up here and the answer. If it's a problem that's marked wrong, what's going to appear in that dialog box is going to be the correct answer. So I get a lot of messages from people saying, hey, I marked this one wrong, but when I looked at it, my answer looks correct. Well, that's because what it's showing is the correct answer. If you take the mouse and you put the cursor, you hover over it with the cursor, then your answer will pop up. You entered, and it'll say what you entered. So if you're reviewing them, that's something to keep in mind, is what shows up there is the correct answer. You have to click on it or hover over it with the mouse to get your answer to come up so you can see what you answered. But it happens all the time where people put in a period instead of a comma for a number, or they hit an extra space or something like that when they're doing a number, or hit the decimal point twice. Let me know on those and I will give you those points back. I'll just go ahead and manually change the grade. Anything else with the inequalities? Okay, as we get going with these, we are going to run into inequalities that are more complex than that. We'll run into things like 9 is less than or equal to 2x plus 1 is less than 23. And we're not going to get too far into these today. I just kind of want to introduce you to them. They will come around, cycle around. There's really 2 inequalities here. There's this one, the first symbol and what's on either side of it, which is 9 is less than 2x plus 1. Then there's this second one over here. The second symbol, the second inequality, which is the 2x plus 1, is strictly less than 23. Now, the nice thing about both of those inequalities is the steps to solve them are the same. In both cases, I'm going to subtract 1 from each side, and then I'm going to divide by 2. So in the left one, it's 4 is less than x. On the right side, again, same step. Subtract 1 from each side and divide by 2. So x is less than 11. And the reason that's so convenient is going back up to this original problem, knowing that those steps are going to be the same allows us to solve both of them at once. I can subtract 1. I have to do it all the way across in all 3 spots, giving me that 8 is less than or equal to 2x plus 1 is less than 22. And then divide by the 2. Oops, the 1 plus 1's not there anymore. Then we divide by the 2 in every spot. So 4 is less than or equal to x is less than 11. And then we, of course, at this point, we do still have to separate it to get both answers, both results. The 2 results that we got down here are what we would get by splitting this up into the first symbol and the second symbol. And this one is good the way it is. What do we have to do to this first one to make it usable, to make it graphable? Flip the sign. So x will be, what's the rest of it? Perfect, greater than or equal to 4. So we could graph this. We would have 4 right here, open or closed? Closed, left or right? Right. Then for this one, we've got the 11 up here, open or closed? Open, left or right? Left. There's a lot more behind those. Like I said, we'll get into it later, of conjunctive or disjunctive is the fancy words, or intersective or intersective. Sorry, intersective or union. In other words, is it an and or is it an or? In this case, where they're all listed together, it's an and, so we have to have both solutions true at once. So how do we combine those 2 solutions into one? Or if it's an or, then either of them is true, so we have to display all of the solutions to it together at one spot. Excuse me. So that's where we're going to be going with that at some point coming up in the near future. Anyway, for now, we've been talking about graphing, displaying data, displaying numerical values on a graph, simply with the number line. We've displayed single values, like this. What's that correspond to? 2, good. 2 or x equals 2 if you want to get fancy about it. Or we could display ranges of values like that. What does that represent? What's that? X is greater than 7. Perfect. Or this one here would represent perfect. X is less than or equal to -3. All of those are simply representing one value, one variable, and its possibilities. Here, X has to be 2. That's the only value that's available for X. Here, X has to be larger than 7. It can't be 7, it has to be larger than 7. Those are the values that are available for X. And the same here. But in all those cases, we're only looking at one value or one variable. There are a lot of times in math where we have values that are linked together and we want to represent them together. Come on. There we go. We might have, after 3 hours of studying for a test, your score improved 7 points. And we want to display those two values together, that there's a link between them. Now, we looked at data graphs yesterday a little bit, and those data graphs did show links between one variable and a value. We did mostly categorical data where we had like colors or some other option, and then its numerical value that went with that color. Here we're pairing two numerical values. We express them like this, and we call it an ordered pair. The pair part should be inherent there. It's a pair because it's a pair of numbers. There's two numbers there. Ordered because the order matters. In this case, the first number is the hours studying, and the second number is the improvement in the score. So we can put them in an ordered pair like that, and expressing them in a table would be rather simple to do. Never mind my sloppy handwriting. You have 3 hours studied, 7-point improvement. I might add somebody who did 4 hours studied and had an 8-point improvement. Or 5 hours studied but had an 11-point improvement, and so on. So we can express those values in a table, and all of them, of course, will give ordered pairs. This one we said was 3, 7, and 4, 8, and 5, 11. And each one of those pairs, notice the first number represents the hours studied, and the second number is that improvement in the score. But even that table is inefficient and not quick to reference. One of the things we talked about yesterday about graphs, the strength of them is that you can reference values very quickly. You can find the largest value, or you compare two values to see which one's bigger or smaller. Triangle link, let's keep that 3, 7 in mind here. Efforts were made historically to do that on a number line. Where they might mark the 3 and a 7. But not only did they have to show the values, they had to show the link between them. You can connect them with a bar, an arch connecting the two of them. But it's not enough to connect them. You have to know what order they come in. Is that 3, 7, or is it 7, 3? Had to put an arrow on them. Well, you can see if I have a lot of pairs like this, our next one was 4 hours of studying was 8. Yep. And 5 hours of studying was 11. Well, you can see that it gets cluttered very quickly. Even with me using different colors, it starts to get kind of difficult to make out the separate ordered pairs. All one color would get very, very cluttered. Some efforts were made to use two number lines. First number line represented the hours studied. Second number line represented the improvement. So we might have 3, 7. But we still had to link them, so we had to have those lines connecting them. And again, you can see how this gets cluttered somewhat quickly. So a better solution was proposed by a man by the name of Rene Descartes. And ended up being referred to as what we call the Cartesian coordinate system, or sometimes rectangular coordinates. And the way it works is what Descartes proposed, I'm going to have to drop a page here, was that we still use that number line like we always did. 0 somewhere in there, we're numbering positive to the right, negative to the left. And we treat that as our first value. Now, depending on what textbook, the old way of referring to this is to call that the x-axis. It's that first value. Others refer to it as the independent axis. Some modern statistics textbooks call it the predictor axis, and the other one is the response axis. The second axis, Descartes took a second number line, but instead of putting them side by side, he found the 0 point of that first number line, and he went vertically through it with a second number line with positive values going up and negative values going down. This one was referred to as the y-axis, or again, sometimes the dependent axis. The reason it's called, excuse me, can't talk today. The reason it was called the dependent axis is it was usually the variable that was influenced by the first one. For example, if we did height and weight, you would want to put the height on that horizontal axis and weight on that vertical axis. Why? Well, does putting on weight cause you to increase in height? Not really. I've put on a lot of weight in the last few years. I haven't got any taller. But does getting taller, does increasing your height tend to increase your weight? And yeah, for the most part, as you grow taller, you do become heavier. So the height has an effect on weight. Weight doesn't necessarily have an effect on height. So the height is the independent axis. It can change on its own. The weight is the dependent axis, even though it can still change on its own, but some of its change is determined by the other variable, by the height. So then let's graph. If this is our hours studied here, is our x, and our improvement is our y. Let's graph that 4 hours and 7% improvement. So we found 4 for the hours is right there. 7 for the improvement is right there. We projected them out until they met. That point right there represents 4, 7. Because its shadow falls on 4 on that x-axis or independent axis, and it falls on 7 on that y-axis, the vertical axis. Now, I'm not going to spend a lot of time on this because I'm sure you guys have plotted points before. Some vocabulary, of course, though. This point at the center here is referred to as the origin. It is the 0 point of both number lines. It's the origin because that's where everything starts for both number lines, from 0 and goes out from there. So if I put points on here like this, what would the coordinate of that point be? 6, 2. Very good. How about that one right there? 0, 4. How about that one? Negative 4, 3. Perfect. How about that one down there? Negative 2, negative 5. Good. And this one here? 2, 0. There we go. 2, 0. Now, we do have instances where we plot separate points like that, but in most cases, we're using one of these graphs to plot a set of points that are related. Where do those points come from? Well, we're going to step back for a second and review solving equations. We might have something like this. 7 equals 3x plus 1. How did we solve that equation? Subtract 1. So we got 6 equals 3x. And you're absolutely right. We divide by 3. So 2 equals x, or x equals 2. Well, we can have an equation like this. 19 equals 3x plus 1. How do we solve that equation? We subtract 1 to get 18 equals 3x. And yes, once again, we divide by 3 to get 6 equals x, or x equals 6. Well, there is a number of equations that all have that same form. And the steps to solving all of them would be subtract 1, divide by 3. Those are called a family of equations. And the way we represent that family is like this. Rather than having this number up front, is we change it to simply being y equals 3x plus 1. And we can solve that whole family, or display, I should say, the solutions for that whole family all at once. This is saying no matter what value that I put in there for y, I can find a value for x that'll make it true. Or sometimes it's simpler to think of it the other way around. No matter what value I put in there for x, it'll give me a valid value for y. We can't possibly list out all of those solutions because, as we said, no, any value I put in there will give me a value for the other variable. So we have to come up with some way of approximating or displaying those solutions. So we have the equation y equals 3x plus 1. One way to display some of those solutions is with a table. I can pick values for x and find values for y. Now, typically my table would be symmetrical. It would only be out to about here, so I could fill in my numbers for y. I made it a little wider on that right side so that I got room to do some work, some calculations. I want to pick a variety of values for x to put in there to find values for y. So I might try x equals negative 3, x equals negative 2, maybe x equals 0, maybe x equals 1, maybe x equals positive 3. So if I come up here, if x equals negative 3, to find y equals 3 times x, that becomes 3 times negative 3 plus 1. Well, what's that end up being? Negative 8. 3 times negative 3 is negative 9, plus 1 is negative 8. Giving us the ordered pair, x is negative 3, when y is negative 8. If x is negative 2, we do the same thing. I'm not write the y anymore, but it becomes 3 times negative 2 plus 1. What's that calculate out to be? Negative 5. Good. So when x is negative 2, y is negative 5. We have another ordered pair. If x is 0, y is 3 times 0 plus 1. What's that come out to be? 1. So again, x is 0, y is 1. If x is 1, y is 3 times 1 plus 1, which is 4. So the ordered pair, x is 1, y is 4. And if x is 3, it's 3 times 3 plus 1, or 10. Giving us that pair, x is 3, y is 10. Now that graph only displays a few of the points. I'm only able to list out, 5, 6 values or so. So I'm drawing out a table here, or a graph here, so that I can take those values from the table and put them on the graph and see if they form a pattern. And in this case, they do. X was negative 3, y was negative 8. So x is negative 3, y is negative 8. Somewhere in there. X is negative 2, y is negative 5. So negative 2, negative 5. Somewhere in there. X is 0, y is 1. So 0, 1. 1, 4. And 3, 10. And I see as I plot those points that those points all form a line. So that graph is a line. I'm going to connect those points and I'm actually going to put arrows on the end to display that line keeps going. Well, what does that line represent here? It represents, go ahead. Well, yeah, it's representing the y equals 3x plus 1, but what about it is it representing? Perfect. All of the numbers x and y that make that equation true. Perfect. If I go on this line and pick any point on that line, let's say I pick a point right here. If I trace that down, I get x equals 2. I trace it over, I get y equals 7. That's the point 2, 7. Is that a solution to this equation? Yeah, if x is 2, y would be 7. I might pick a point right here. X is negative 1/2. I drew that poorly. It'd be actually right there. X is negative 1/2. Y is actually negative 1/2. That point is negative 1/2, comma, negative 1/2. Would that make this true? It sure would. Any point on that line, if I find its x and y coordinate, in other words, if I find the ordered pair that it represents, that ordered pair is a solution to that equation. That line is all of the possible solutions. Now, not all graphs form a line. This one was simple. We did 4 or 5 points. We put those points on the graph. They made a line. We just drew the line through it. We were done. Not all equations form a nice line like that. We can run into equations like this. Y equals x squared minus 3x minus 4. We can pick points for this, and we can pick values for x and come up with values for y. But it's not going to be quite as simple as it was before. So let's start out with x and y here. I'm going to pick some values for x, and then I'm going to figure out what y has to be. So if I put in x equals negative 2, Y then has to be, I put -2 in for x, so -2 squared. Remember the parentheses around the negative when you square it so that it doesn't give you the wrong value in your calculator. Minus 3 times -2 minus 4. When we calculate this out, -2 squared is +4. I'm going to treat this as a -3 times a -2 is a +6 minus 4. 4 plus 6 is 10, minus 4 is 6. So when x is -2, y is 6. I'm going to go ahead and put that point on my graph because it's not like a line where it doesn't matter what points. It's going to matter what values of x I pick here. And having points on the graph help me figure out what values of x to use. So I'm going to go at -2, 6. Right there is that point. I want to see what happens. Let's move to the left a little bit. I'm going to pick an easy point. It's usually an easy one to use. X equals 0. Now again, the -2 and the 0 are points that I just picked to see what they give me for y. We'll go back later and figure out what other values of x we have to use. So if x is 0, y is going to be 0 squared minus 3 times 0 minus 4. What's 0 squared? 0. What's 3 times 0? 0. So 0 minus 4 is -4. So when x is 0, y is -4. That gives me that point on the graph. Well, that's quite a change. Let's see what's going on as we keep moving to the right. Let's try +2. If x is +2, y is 2 squared minus 3 times 2 minus 4. I'm going to pause here. Any questions on where this came from? Highlighted there? That's just the equation. I put 2 in where the x was at every spot in that equation. So we have 2 squared, which is 4. Minus 3 times 2 is minus 6. So we've got 4 minus 6 minus another 4, which is -6. So when x is 2, y is -6. So 2, -6 is right there. Well, looking at those 3 points so far, my point moved on me. It's pretty obvious from just those 3 points this is not a line. They're not straight lined up, are they? So we're going to pick more points. The question is, where do those points need to be? Well, I'd like to know what's going on between these two. Or that rapid drop, does it go straight or is it curved or whatever? And I want to know what's going on over here yet. So I'm going to start, I'll pick these larger values of x to fill in over here. Again, I'm getting these values because I need to know what's going on over here so I know what shape this is so I can draw it in. So I'll come back over here. What should we try? X equals 4, maybe, see what that does. So if x equals 4, in your notes, I want you to try to figure out what y is. What'd you get for y? 0. So when x equals 4, y equals 0. Well, now we're definitely sure it's not a line. So I want to know what's going on over here yet. We'd like to know what's going on between these 2 points, and then I still need to go back over here. So let's do that -1. Let's fill in this gap over here next. So if x equals -1, again in your notes, try to beat me to it. Figure out what y is when x is -1. It's actually 0 again, isn't it? So x is -1, y is 0. So -1, 0 puts us right there. Well, we'd like to know, oops, my 2, -6 disappeared again. There we go. We'd like to know what's going on here yet. Maybe still at 1 and at 3. Let's figure those out. Let's put in 1. So I want you in your notes, find out what y is when x is 1 and when x is 3. Perfect. When x is 1, y is -6. Yep. When x is 3, y is -4. So we've got 1, -6, and 3, -4. Let's put those out here, see what it looks like. So 1, -6 is right there. 3, -4 is right there. Now we're starting to get a picture here of what this looks like. You might pick more points if you wanted to be sure. But we can tell it's going to look something like that. There's a name for this. It's called a parabola. We're going to look at them more as we go on in the course. The type of equation, an equation that has x squared in it like that, is called a quadratic. And again, we will look more at quadratic equations later on in the course as we go through. So looking at our graph, some terms that will come up are the quadrants. That graph is divided with those axes into 4 pieces. This here is usually referred to as the first quadrant. A lot of textbooks use the Roman numeral 1 instead of just the number 1. It's called the first quadrant because that's the one that pretty much always gets used. Both the horizontal and vertical variable are positive there, or if you're using x and y, both x and y are positive. From there, it really doesn't matter which direction we go, whether we went clockwise or counterclockwise. But there are other things in math where we go clockwise around, like for trig and stuff like that on the unit circle. So this is referred to as the second quadrant, third quadrant, and fourth quadrant. The reason I bring them up is just human nature. When I ask you, get back here, when I ask you to pick points for x and plot points to try to graph it, most people are going to pick positive values for x and put them in there. But on this one here, it would have been really tough to graph it with only positive values of x. You need to work in the second and third quadrant, in other words, negative values of x, in order to get a good picture of most of these graphs. Now, if the class had the timing were different, normally what I would do is I would send you home with a worksheet like this one here and have you do it as part of your homework and would use it to discuss. In fact, this worksheet is in Blackboard. It is in the February 4th through 6th. It's in there with the recording links. If you would like to download that worksheet and complete it, it would help your skills as far as constructing tables and graphing. But what I'm going to do right now is I'm going to go through it with you and give you the basic shapes of the graph so you know what those graphs should look like. There, it fixed the format a lot. So for the first one here, y equals 3x minus 2. I'm not going to put points in the table. The table is there. You can put points in it if you'd like to, but it gives us a line that looks something like that. You'll notice on the end of the line, I put arrowheads pointing in both directions. Why are there arrowheads there? Yeah, it keeps going in both directions. The values of x and y can keep getting larger and larger as we go that way, or smaller and smaller further into the negative as we go the other way. The second one over here, y equals 6 minus x. It's going to look something like that. Again, the arrowheads, we can keep going in both directions. This next one, y equals x squared plus 2x plus 1, we should recognize that. What word did I just put with that? Whenever it says x squared, it's called a quadratic. Very good. And quadratic equations form parabolas. This one happens to look like that. Again, notice arrows on both ends. The values here, the values of x could keep getting bigger and y would keep getting larger, or the values of x could keep getting smaller over here and y would keep getting larger. Number 4 is the last one we'll do with you here, and then we'll get to the point. Number 4 could look something like this. You'll notice on number 4, I put an arrowhead here, but not on this end. Why not? Yeah, it doesn't keep going that way. That would be x is negative 6. If I put negative 6 in for x, y is the square root of negative 6 plus 6. What's negative 6 plus 6? 0. Square root of 0, of course, is 0. If I kept going to the left side, if I put in negative 7, what's negative 7 plus 6? Negative 1. What's the square root of negative 1? Well, we did it in your calculator is going to say error, isn't it? We can't do the square root of negative 1. Now I'm going to qualify this with for a second, because in about 10 or 11 weeks, we're going to do the square root of negative 1. In real numbers, you cannot do the square root of negative 1. You'd have to use imaginary or complex numbers. So the reason there's no arrow on the end here is this: the values of x cannot get smaller than 6. If x is smaller than 6, we're trying to take the square root of a negative number, which doesn't work. So as we look through this worksheet, I'm just going to circle the ones here that form lines. We saw 1 and 2 formed lines. Get a decent look at those equations. As we go down here, these neither one formed lines. 5 will make a line. 6 will not. 7 and 8, either one of those will. 9 will not. This 10th one will make a line. So I want to list the equations here of graphs that were lines. So the ones that were lines, we had y equals 3x minus 2. We had y equals 6 minus x. Y equals 3 minus 3x. Let me double check that one. 3 plus 3x. Sorry. Y equals 3 plus 3x. And y equals 3/4 x minus 4. Those all formed lines. We have equations there that don't form lines. Y equals x squared plus 2x plus 1. Y equals the square root of x plus 6. Y equals 2 to the power of x. Y equals x to the third minus 1. Y equals, I think it's 4x squared minus 8. And y equals 8 over x. Those are the equations that did not form lines. What I want you to do is take a minute to look at those equations and tell me what's different about them. In other words, what appears in these equations that does not appear in these? What could I look at here and see that makes those not be lines? Take a minute. We'll discuss it here in just a minute. So what do you see in these equations that you don't see in the lines? What's one of the things you see? Exponents, okay? You got x squared here, x to the third, x squared. An exponent on the variable. I'm going to put down other than 1. Because technically, this is x to the power of 1 in each of those. Included with that, by the way, is this here. That square root is actually an exponent. It is a power of 1/2 that we'll see as we study exponents more closely. But it's not a 1. What else do we see? X is part of a fraction, but it's not that it's part of a fraction, it's where it is in the fraction that's important. Where is it? It's in the denominator, yes. It's in the denominator, or we're dividing by x. Divide by a variable. And we'll put in there or in denominator. The last one, this one here, what's going on there? X is the power of the exponent. So a variable in the power. Notice all of those things have to do with powers. That variable in the denominator, at some point we'll see that actually could be thought of as a power of -1. Dividing by something and be thought of as doing a negative power. These three things are what I refer to as the 3 don'ts of linear equations. Because they are the 3 things that linear equations don't have. So using those, I can very quickly look at an equation and decide if it's linear or not. Is that equation linear? Yes, it can simplify to y equals 9x minus 14. That's linear. How about be careful on this one. That can simplify to y equals 8x plus 3. So yes, it is. This one. No, there's x squared and it doesn't cancel out when we do anything to simplify it. How about this one? Why not? 3 to the power of x. Very good. How about that one? Yeah, that just simplifies to y equals 9/5 x. That is just fine. How about that one? Yep, that simplifies to y equals 3x plus 32. That is just fine. How about that one? Why not? We're dividing by x. Perfect. So we can look at equations and we can tell rather quickly whether it's going to be a line or not. What happened there? So anyway, now that we can tell that it's going to be a line, there's other things that we can work with. We'll look at shortcuts for the line. Before we do that, let's look at testing solutions. So if I give you an equation, y equals 3x squared minus x plus 4, and I ask you to test the point 2, 14. Is that a solution to this equation? Well, to test it, 2 goes in for x. So that's 3 times 2 squared minus 2 plus 4. And 14 goes in for y. Now, I really shouldn't put an equal sign in here because I don't know if they're equals. So really, right now, I have to treat both sides as separate problems. The left side is just 14. There's nothing else over there. On the right side, I have to do my order of operations. What would be the first thing we would do? The x squared, the 2 squared, I should say, which is 4. Now we have to multiply 3 times 4, which is 12. And then subtract 12 minus 2 is 10. 10 plus 4 is 14. We get the same value on both sides. 214 is a solution to that equation. In your notes, test and tell me, is 1/6 a solution to that equation? So the left side is just the 6. On the right side, we do the 1 squared is just 1. 3 times 1 is 3. 3 minus 1 is 2. Plus 4 is 6. It does work. Test that one to see if that's a solution to that equation. I'll give you 30 seconds or so in your notes. So we put x in, negative 1 in for x, so 3 times negative 1, minus 2 times 5. Oops, you're right. I screwed it. I did it backwards. Thank you. 5 in for x, negative 1 for y. Good catch. 3 times 5 is 15. Now, I could either treat this as minus 2 times negative 1 or negative 2 times positive 1. If I treat it as minus 2 times negative 1, that's minus a negative 2, which is going to become plus a positive 2. If I did it as negative 2 times negative 1, it'd be plus 2, so it gets the same thing. That comes out to 17. That is not a solution. They're not equal. So we know certain equations have to form lines. The next step is to start looking at linear equations and shortcuts for graphing them. We're going to cut it off just a little bit early today because I'm supposed to be in a meeting right now, but I skipped out to teach this class. So this is where we're going to pick up tomorrow. We're actually right on schedule anyway. You do have homework 3B that pertains to this material. Does anybody have any questions before we go? Okay, well, you guys have a great day. Just a little bit of a warning about, this is the third, it feels like we just started the semester because of all the days off. This is the third week of the class. So 3 weeks from yesterday will be our first midterm. So that means coming up on February 25th is our first midterm. If you go into Blackboard, I don't know if I got it posted or not. I will have it posted very soon if it's not there right now. I'm going to check right now. So the test is sitting there. I will have posted here before the end of the day, I will put out a study sheet for test 1. It wouldn't be a bad idea to print that off and start working on it just so you've got the concepts down. We will start covering a lot of material fast now that we're hitting full pace. So I suggest you keep up preparing for the exams. Okay, so with that, I'll let you guys out of here. We'll see you tomorrow. You guys have a great day.